is, oh, you can't see that, proportions in triangles. I don't know. Okay, here's the deal. I have two theorems for you today, and everything pretty much hinges on those two theorems and what we do with them. So the first one is called the Side-Splitter Theorem. Okay, Side-Splitter Theorem. Basically what it says is if you have a triangle and you draw a line that is perpendicular to one of those sides of the triangle, it's going to break the other two sides into proportional sides, okay? And I'm not going to write out the definition of the Side-Splitter Theorem. If you would like to, it's in your book, but I feel like the picture tells you what's happening. So I'm going to draw you a picture and then just label what exactly is happening here. So let's say we draw a line parallel here. You need to pretend that looks parallel because it doesn't. Try again. Okay, so if I have these parallel lines, and this is A, B, C, D, and E. Okay, the theorem says this. If BD is parallel to AE. Okay, so if they are parallel, which is what I have drawn for you, that they are in fact parallel, then we can say that the sides are proportional. So then it would be true that AB over BC would equal, can you guess what the other side then should be? If it's AB over BC, it should be what?
ED over DC.
ED over DC. Okay, if it helps you to see it in letter form instead, if we said this is W, X, Y, and Z, you could say W over X, or X over W, right? Properties of proportion says you can flip that over. So W over X equals what? Y over Z. Okay. So before, we always said you have to add the two sides together and add the two sides together. Well, now because we have this parallel line, you don't need to call it W plus X over X. You can just say W over X, okay? Because we have that parallel line. That's called the Side-Splitter Theorem. It's splitting the sides proportionally, okay? Questions on that? Okay. I'm just going to prove to you why, just the reasoning behind it. You don't need to draw this, okay? This is just a proof of this theorem, and I'm not even going to write out the proof. I'm just going to walk you through why it works. So let me just draw you another picture here of the reasoning behind this. So if I know these are parallel, okay? Parallel lines often get us angles that correspond to each other. In this case, actual corresponding angles, right? So I know these two angles would be congruent, and I know these two angles would be congruent. So right now, I know the small triangle and the big triangle are similar triangles, right? By AA similarity. So because I know those are similar by AA, and I know that this side plus, I should give you letters, these two added together, right? That's angle addition postulate would say AB plus BC equals AC, okay? And it would say that, we'll call this D and E, AD plus DE would equal AE. That's segment addition postulate, okay? Well, what happens is because I know the properties of proportions, remember the property of proportions that was on, she hasn't taken the quiz. Here's a little heads up for you. Remember how we said if you have AB over BC equals AD over DE, technically you're allowed to say that AB plus BC over BC is equal to AD plus DE over DE, right? That's a property of proportions. okay? Seriously, you don't need to write this down. Just watch. If that's the case, then I can go the opposite way with it and say, because I know segment addition postulate, because I know this is true, then I know that this is true because I'm allowed to take BC and DE out of it and just say that AB over BC will equal AD over DE, okay? So yes, segment addition or side-splitter theorem says this, but the only reason we know side-splitter theorem says this is because this property of proportion came into play, okay? Don't let that confuse you. It's just why side-splitter theorem works. You need to know how to use side-splitter theorem, which is just setting the sides proportional to each other, okay? Okay, let me show you an example of what you're going to do with that. Let's say we have this triangle. Sorry for the squiggly lines. Got myself a chai tea latte this morning, and that just always makes me jittery, which is ridiculous because there's hardly any caffeine in those, but that's how little caffeine I drink ever. So good. I got one from Coffee Bean and Tea Leaf at Monster Jam, though. Theirs are not as good. Like, Starbucks chai tea lattes are they're just better. Okay, anyway, if this is our setup, what would side-splitter's theorem say right now? What to what equals what to what?
4x minus 2 9, 3x plus 2.
Okay, so you can do it either way, right? You can say 9 over 4x minus 2, or you can say 4x minus 2 over 9. What matters is that you stay consistent. So if I'm going to start at the bottom and move to the top, then I need to start at the bottom and move to the top on the next one. If you're going to start at the top and move to the bottom, then start at the top and move to the bottom again, okay? So it's not wrong to flip this whole thing over. That's properties of proportions. All right, so we cross multiply that. 9 times 3x plus 2 equals 12 times 4x minus 2, and now it's just algebra. Distributive property says we have 27x plus 18 equal to 48x minus 24. Okay, simplify again. We're going to take away that 27x. So this is gone. We're going to move that 24 over. Good old algebra. So you get 21x here equals 42 over here. And then divide by 21. And x should be 2. Okay, that is side-splitter theorem. Any questions on that? Okay, I have one more of those if you would like it. You want one more? Good on that? Okay, if you want another one, I can come back at the end and do another one for whoever wants it. There is a corollary to the side-splitter theorem. And so corollary, remember, that's just an add-on to the theorem. So another detail that works, but you're doing the theorem the same way. Your picture's just going to look slightly different to start. And that looks like this. If you have parallel lines instead of triangles, okay, so let's say these lines are all parallel, and we have a transversal here and a transversal here. If this is A, B, C, and X, Y, and Z, okay, notice these are not triangles. The rule works the same because you have the parallel lines. So the setup would be this. If, we're going to call this line H, line I, and line J. So if H is parallel to I, which is parallel to J, which in this case it is, right? We put the arrows in to show that they're parallel. Then we can say that AB over BC should equal what? Yes, XY over YZ. Okay, so the portions over top of each other. This over that equals this over that. Okay, And this only works if the lines are parallel. If the lines aren't parallel, you can't use these theorems. Questions on that? Okay, so let me give you an example that looks like that. This would be example 2. And this doesn't look exactly the same, but it's the same idea, so make sure you're seeing it. If you're not, let me know. Oops. Okay, so no triangles here, but we have the parallel lines. What parts get put over top of each other? If I started at x over what? 62. So I turned it, right? All I did was rotate the parallel lines. So it's the two that are on the same line that you put over top of each other. So x over 62 should equal what over what? 70. So because I started here, then down here, I have to start here. Okay, so x over 62 should be 70 over 56. And then you would cross multiply that. So 70 times 62 is 4,340. And that's going to equal 56x. So we're going to divide by 56. And that comes out to 77.5. Okay, now here's a beautiful thing for you. Not that I'm encouraging you to do things wrong, but properties of proportion says you can change your means. And a lot of people see this problem and they say, oh, x over 70 equals 62 over 56, which is not correct, but guess what?
It is.
You're going to get the right answer. Okay, so there's one beautiful little perk to properties of proportions, that you can do it wrong and still get it right. Okay, I'm not encouraging it. I'm just telling you, when you get confused because mine looks different than yours, but we got the same answer, that's why. You just put yours in a different property of the proportion. Any questions on that one? Okay, the last theorem then is called the triangle angle bisector theorem. Okay, and the triangle angle bisector theorem looks like this. If I have a triangle and I bisect this top angle, okay, so this has to be the case. If you have an angle bisected, then this theorem will work. Okay, we're going to call this A, this B, this C, and then the point where the angle bisector hits is D. All right, here's what it says. If ray AD bisects angle CAB. Okay, so if in fact this is an angle bisector, which we're showing in this picture that it is, so if AD bisects, then what happens is I can say CD over DB will equal, any guesses? If I say CD over DB, CA over AB. Okay, and this one can get a little confusing to people at times, so here's what I always tell people to think of. The two that are forming a straight line are the two that get put over top of each other. Okay, so CD and DB form that straight line, put them over top of each other. Then you just have to make sure that because I started on the left and went to the right, I go back to my left and then put it over the right. So don't go left to right equals right over left. Okay, has to follow that same order that we always follow. Questions on that one? Here's a problem for you. Okay, and you have to pay attention to this. This is what tells you how to set the problem up. Do I have parallel lines or do I have an angle bisector? This one we have an angle bisector. Okay, so with an angle bisector like this, if this is x, 25, 15, and 9, how do I set it up? And again, properties of proportions saves a lot of people on this problem because a lot of times people are tempted to go the other way with it. Sam?
9 over 15 equals x over 25.
Right, so the two that form a straight line get put over top of each other, 9 over 15, and then just be very careful. You started with the 9, you need to go back to that triangle for your top number again. So if it's 9 over 15, then it's x over 25. Okay, cross multiply that, you get 15x equals 225, and then we're going to divide by 15. So x is 15. Okay, indeed.
Whoa.
Any questions on that? So those 2.5 theorems, because you have the corollary, right? And they're really just setting up a proportion. So if you can see the sides that would be similar, you're in really good shape, okay?